Okay, so we're looking at question 22 from section 4.3. It says h of x equals x squared minus 1 cubed. So what I like to do first is to find both the derivative of h of x and the second derivative. So we'll start with that. And we can see that we're going to have to do a chain rule. So we'll get 3 times the baby times the derivative of the baby, which is just 2x, which can be simplified to 6x. And then when we take the second derivative, you can see that we do, sorry, this should also be squared. We have a product rule with the chain rule, so we're going to have to do the derivative of the first, which is 6, times the baby, which is x squared minus 1 squared, plus the first times the derivative of the second, which is 2x, sorry, it should just be 2 times the baby times the derivative of the baby, which is 2x, which can be simplified further. And we can take everything that's outside the parentheses on this next part and add them together, so then we will get 24x squared. And then you see something very important here that will really help us. You can see that both of these are included in each of them, and you also can take out a 6 because 6 goes into 24 here. So what we're going to do is simplify it a little bit better. So we'll take brackets 6 times x minus 1 plus, and you see that it was squared right before, so we need to say plus what was in the parentheses, which is x squared minus 1 plus x squared minus 1 plus 4x squared, which you can take down a little bit even further. X minus 1, close the brackets, x squared minus 1. Sorry, these should be squareds. I actually made a mistake here, so we're just going to erase this here. And it should be, we'll take this out too so we can see a little bit clearer. This should just be plus 4x. 4x squared. And then we can combine like terms, and we will get 5x squared minus 1. Okay, so now that we have this information, it'll be a little bit easier for us to solve the questions. So A says to find the intervals of increase or decrease. And we know that f is increasing if f prime is greater than 0, and we know that f is decreasing if f prime is less than 0. And we found the derivative just before we do h of x, and it's right here. So what we need to do is we need to find when h prime of x equals 0. So we will say 0 equals 6x times x squared minus 1 squared. Separate that, so we get 6x equals 0. And then x squared minus 1 squared equals 0. We can see that x equals 0 if you divide both sides by 6. We can square root both sides. The square root of 0 is 0. So we get x squared minus 1 equals 0. Bring it over. Take the square root. and we see that it'll be plus or minus 1. So then we can come and make a number line here, h prime. And we have zeros at -1, 0, and 1. And if we just plug in some numbers, if we plug in a -2, we'll get a negative. If we plug in a -0.5, we'll get a negative. If we plug in a positive 0.5, we'll get a positive. And if we plug in a positive 2, we'll get a positive. So we can see that h is increasing when I meant this should be h's at the top, but when h prime is greater than 0, and we can see that's happening from 0 to 1, and then from 1 to infinity. And then for decreasing, we can see that it's from -infinity to -1, and -1 to 0. And then, so that means that this is your answer for part A. Part B asks us to find the local maximum and minimum values, and part C asks us to find the intervals of concavity and inflection points. I think that C will be a little bit easier to solve first, because once you know where it's concave up or concave down, you will then be able to find the maxes and mins. So we'll go ahead with part C first. So like we found when we were starting the problem at the beginning, we found that this should be a double prime of x equals 6 times x squared minus 1 plus 5x squared minus 1. Yep. Okay. Sorry, this should be times. Whoops. Alright, so we know that h will be concave up when h double prime is greater than 0. And h will be concave down when h double prime is less than 0. So first we're going to have to set h double prime to 0. So we'll say 0 equals 6 squared minus 1 times 5x squared minus 1. Separate those. We'll solve this one first, divide both sides by 6. We have 0 equals x squared minus 1. Bring the x over here. Equals 1, square both sides, so we get x equals plus or minus 1. Over here, we'll bring the 5x squared over. Divide both sides by 5. Square root, so we're going to get x equals plus or minus square root of 1/5. So then next we will do a number line of h double prime, and we see that we have zeros at -1, negative root 1/5, which is about a 0.44. It's a little messy. A positive root 1/5 and positive 1. And when we plug values in, when we plug in a -2, we'll get a positive. When we plug in a -0.5, we get a negative. If we plug in 0, get a positive. If we plug in a 0.5, we'll get a negative. And if we plug in a 2, we'll get a positive. So we can see that we go positive to negative, max, which will help with part B. You can see a min, max, min. So then we know that h is concave up from -infinity to to negative 1, negative root 1/5 to positive root 1/5, and also from 1 to infinity. And we see that h is concave down when we, between the intervals of negative 1 and negative 1 root 1/5, and then from positive root 1/5 to 1. And so then we also just have to solve for our inflection points, and we know that inflection points are where concavity is changing. So we can see that our inflection points are at x equals plus or minus 1, and when x equals plus or minus root 1/5. So here's your answer for part C. Part B asks us to find the local maximums and minimums. So for B, I think it would be best to take our number line we found from C, which would be h double prime. Make a nice line here. We can use the same zeros. We'll get negative 1, negative root 1/5, root 1/5, and 1. And again, we have a positive, a negative, a positive, a negative, and a positive. So we know that there's a local max when it goes from positive to negative. And so let's see, we'll do this positives in green. So it's going from positive to negative at negative 1 and at positive root 1/5. And it asks us to find the values of local maximums or minimums, not just the points. So we need to plug in. So first, if we plug in f at negative 1, we'll get 0. And if we plug in f at root 1/5, we will get negative 0.512 about. And so then we know that we can also find local mins when we go from negative to positive. We'll do these in red. So we can see that it's going negative to positive at negative root 1/5 and also at 1. So we can plug in, we'll just say f at negative root 1/5 will give us the same number for positive root 1/5, so negative 0.512. F of 1 also equals 0. All right, and that's it.